Okay, last time I had kind of proved the following statement. If you take G semi-simple defined over Q and gamma arithmetic lattice, I had more or less proved this last time. Then there exists finitely many minimal parabolic subgroups defined over Q such that every parabolic group Q parabolic, minimal Q parabolic, is conjugate to one of these by an element of gamma. I kind of sketched a proof. I think I didn't go into the details very well. I waved hands considerably, I think, but you will find a proof in my book for this statement. Okay. I don't want to go into the proof. It's not very illuminating. But the point you want is the following. This is equivalent to saying let P be a minimal parabolic subgroup defined over Q. This statement is equivalent to saying then GQ by PQ by gamma, this double coset set is finite. Let me recall a few things. What is the minimal parabolic, etc., etc. So for an algebraic group G algebraic group, a parabolic subgroup by definition is a subgroup, is an algebraic subgroup P such that G over P is projective. The quotient of an algebraic group by algebraic subgroup is always a variety, and the condition is wanted to be projective. This is also equal to saying P contains a maximal connected soluble subgroup. That's the definition of a parabolic group. Then of course, when G is an algebraic group defined over Q, a parabolic subgroup defined over Q makes sense. The point is that G acts on the set of parabolic groups it's a Borel. Yeah, that's the definition of Borel. It's the definition of Borel subgroup. There is a long paper of Borel and Titz. Consider rationality questions, groups over general fields rather than an algebraically closed field. And in the beginning somewhere they define a Borel subgroup as a maximal connected soluble subgroup. It's a footnote. The first named author did not want this name, but the second author insisted. Much later, there is something, Titch system comes up. Star, it is his turn of the second author to protest. Something like that, to that effect. Okay, G acts on a set of parabolics. Say, yeah, parabolics by conjugation. And the number of this action has finitely many orbits, and each orbit contains a standard parabolic. What do I mean by standard parabolic? Well, I have to go further into the structure. Namely, you start with standard parabolic with respect to maximal torus, maximal, and a Borel subgroup. This means so T maximal torus in G. At the moment, I am working entirely over complex numbers, not no rationality question. T maximal split torus, maximal torus, and then phi roots of T with respect to roots of G with respect to T, and for alpha and phi, G alpha is the eigenspace for T corresponding to the character alpha. Roots are characters on T. It acts through that G alpha in the Lie algebra. We also introduce an order in Xt, which is isomorphic to ZL. L is called the rank of the group. ZL, one introduces so-called lexicographic order. You just take a basis E1, E2, En, ordered basis E1, E2, En. Every element can be expressed as a linear combination of these basis elements with coefficients, and you say the element is positive if the first non-zero coefficient is positive. That's the definition of order. So, lexicographic order. E1, E2, EL, basis of Xt, Xt we know over Z, an element alpha equal sigma alpha ei I equal to 1 to L is greater than 0 if the first non-vanishing alpha I is strictly greater than 0. Now, the entire structure theory for simple groups or an algebraically closed field is developed using the maximal torus and its root system, and one knows that the root system determines the semi-simple group up to local isomorphism, up to isogeny as they call it in algebraic groups. And phi itself, introducing an order decomposes phi as positive roots and negative roots, phi plus union phi minus, where phi plus is the set of alpha in phi with alpha greater than 0, and this is the set of alpha in minus alpha with alpha in phi plus. So the negative roots and the positive roots in this situation. Now the whole thing can be imitated to an arbitrary field. We are interested in Q, so we'll stick to Q, but you can also do it over any field. The thing is this: one starts with, so G semi-simple defined over Q. T, the maximal Q split torus. As I said, you can replace Q by K for many other things I am going to say. Practically everything I am going to say works with any field K. Some other things may not work for positive characteristic, but the characteristic 0, whatever I say here, will work through. Even positive characteristic things I am going to say here will work through. Sometimes they a bit annoying, giving a proof gives some difficulties, but it's so T a maximal split torus. Maybe I'll call this S rather than it. Let me denote by ZS, centralizer of S. In this case, the Lie algebra G has a Q structure, that is, it is of the form a Q Lie algebra, which I call GQ, tensor C, the natural fashion. Now, since T is S is a split torus, with respect to X, you can decompose the Lie algebra into eigenspaces. So, G decomposes as sigma. In fact, GQ already decomposes as GQ alpha, alpha in phi. I'll put a Q here because I am decomposing with respect to Q split torus. So, it decomposes like this, plus centralizer of the torus in the Lie algebra, direct sum sigma GQ alpha alpha in phi Q minus. Exactly as we do here, you decompose the Lie algebra, then it decomposes into positive, you introduce an order on xt, decompose to positive negative. This is the eigenspace corresponding to trivial character. These are non-trivial characters. Let's decompose. And now look at ZS, direct sum sigma G alpha Q alpha in Q phi plus. This I will write as BQ. Rather, sorry, write this as PQ. ZS is the centralizer of S in the Lie algebra, that is those which are fixed by S, 0 eigenspace of S. Not 0, trivial eigenspace. I call this PQ. And in fact, I will also give names. I will call this N plus Q, and I will call this N minus Q. So, you find that GQ decomposes as NQ plus ZS Q. The centralizer of S is the eigenspace corresponding to Q. So, it is a subspace defined over Q of the Lie algebra and N minus Q. And you have corresponding Lie subgroups corresponding to N plus Q. I denote by capital N plus, and this is defined over Q. The Lie subgroup, when I say that, I must first of all tensor with C, take corresponding subgroup, and it automatically is an algebraic group. NQ minus will be similarly N minus, gives you Lie subgroup corresponding to this is again defined over Q, and the centralizer of S in the group EC has, so ZS is Lie algebra of ZS. this is centralizer of S G. You have such a decomposition. Now, if you go to the algebraic closure, inside here in ZSQ plus NQ minus, you will have a maximal solvable subgroup, which will be a Borel subgroup. ZSQ, this is what I call PQ. The group corresponding to Q, group corresponding to PQ. Let's simply call it P. P is a parabolic subgroup defined over, and it turns out it's a minimal parabolic subgroup defined over Q. The point is this, that if you take a parabolic group and look at G mod P, and then take any other parabolic, any minimal parabolic subgroup, it will have a you take its unipotent radical, that will be an algebraic group defined, unipotent group defined over Q. It operates on G by P, and it will have a fixed point on, see, so start with, take G by some parabolic P1, this is defined over Q, and then you have UQ, I call that n plus. Take a minimal parabolic, look at the action of n plus on G by P1. This action has a fixed point. The Borel fixed point term works here. The point is, it has a fixed point, it's a Q rational point. You can get a Q rational point, which is, and this is essentially done. The point is that G over P1 itself has plenty of Q rational points, because what happens is this P1 is a parabolic group, so it will have a unipotent radical n1 plus, and if you fix a maximal reductive subgroup, you will also get a supplementary thing stable under that, so that it becomes, the whole becomes n1 minus plus P1 plus, and the n1 minus is a unipotent group defined over Q, and so it will have plenty of rational points. Take the Lie algebra, take rational point, they exponentiate. Since the exponential series terminates, you land in a rational element. So because of that, this becomes consists entirely of rational elements, which means in G over P1 there are lots of rational elements, because n1, the corresponding group n1 minus, take an orbit of the identity element, all, and the Q rational points will go into Q rational points. So plenty of Q rational points. Now fix up Q rational point and make this n plus, the unipotent radical of a minimal parabolic, operate on it. Then it has a fixed point, is what you say, and this is done by induction. First, n plus has a series descending surfaces. Take the center and take a one parameter subgroup in the center. You look at the action of the one parameter group defined over Q. The center becomes a vector space, and so it will have plenty of one parameter subgroups. Then you look at the orbit. The orbit has exactly one. It's a mapping into the complete varieties, so it has the valuation criterion tells you the point at infinity. You get that will be a fixed point, and that fixed, obviously it's stable under the Galois action, because this n plus action is stable under the Galois. The open orbit is stable, closed orbit is stable, so the one point which is missing is also stable. So it's a rational point, and so you get and then you argue by induction. So it says, if you take a unipotent group acting on a projective variety, and then the orbit of any take the orbit of any point, its closure will contain a fixed point. That will be the statement. You just do it by induction. Okay, so all this tells you that there is this parabolic group, minimal parabolic group, and it tells you immediately the minimal, all the minimal parabolics are conjugates to each other, because you take the unipotent radical of minimal parabolic, apply it on G mod another minimal parabolic, it has a fixed point. So it, after conjugation, it falls into P. Once it falls into P, you can, it's quite easy to see it has to fall into the unipotent radical of P. It work a little bit, and therefore the unipotent radical goes into the unipotent radical, and the parabolic can be characterized as the normalizer of its unipotent radical. So parabolic can be conjugated into standard parabolic. Under GQ, all minimal parabolics are conjugates. And then the statement we want here is that, so on minimal parabolics GQ acts transitively, and what is the isotropy? Isotropy is normalizer of parabolic group. Normalizer parabolic group is itself, it's one of the standard results, basic results. So GQ by PQ gives you the set of parabolics defined over minimal parabolics defined over Q. Sorry?
I did my Humphrey's book read the any parabolic subgroup are conjugate.
Any parabolic subgroup?
Are conjugate.
No. See, over algebraically closed field, not all parabolics are conjugates. What happens is that the minimal parabolics are conjugates. In the case of algebraically closed field, the Borel subgroups are all conjugates. There are several parabolic groups containing the Borel, and there are only finitely many distinct parabolics containing the Borel, and any parabolic is conjugate to one of these. That is the correct statement. Okay. All right. So this GQ by PQ by gamma is finite. It simply says that if you look at the conjugacy classes under gamma of the parabolic group, there are only finitely many of them. Every parabolic defined over Q is conjugate to one of a finite number of parabolics under gamma. Okay. In the case of when G is SL and R for instance, there is essentially only one Borel up to conjugacy. The reason is that a Borel is simply given by a flag, a filtration, and you can find a basis which is Z basis which is compatible with that filtration. Take another flag, take Z basis, and this Z basis can be taken to that Z basis. That will take you, the flag will take you to the flag, and therefore there is only one conjugacy class of parabolics defined over Q. All flags over Q is what I am working with. That is a very special situation. In fact, already if you take GLN or SLN over number field, it will fail. What happens there is SLN over number field, the number of elements, number of distinct conjugacy classes of Borel subgroups are in bijective correspondence to the ideal class group of the number field, the Hilbert class group. Like the class number is the number you need there. So that is why you need finite numbers, you cannot escape that. Even for GLN, SLN, you cannot escape that. Okay, all this, and now a little more about the structure. I start with the group G or G over Q, semi simple. And then look at the R points. This is a real semi simple D group. It has, let K be, let P be a maximal a minimal Q parabolic of G. Let K be a maximal compact subgroup of G, of GR. Then one has the following fact: G equals GR equals K times this is a consequence of the so-called Iwasawa decomposition. The point is that over R, this parabolic group contains a smaller group, a parabolic group defined over R, and a parabolic group defined over R looks like A, which is, there's the Iwasawa decomposition KAN. You look at A, centralizer of A part is really A times something in the compact group. So KAN is the Iwasawa decomposition. N is in the unipotent, N is in the unipotent radical of the big group, which means it's also going to be in the parabolic group PR. So this decomposition will follow from Iwasawa decomposition. Okay, and the point is that n is completely contained in PR and A is also contained in PR. So KPR, no, this is here it's a homeomorphism, but not here. There will be some intersection. K intersection PR is same as centralizer of this part. Sorry, ZS. Okay, ZSR intersection K. ZSR is contained in PR. PR intersection K is actually contained in the intersection of ZSR and K. There will be a, even in the Iwasawa decomposition of KAN, what A is the element, A consists entirely of elements of split torus over R, and its centralizer is somewhat bigger. There could be a compact part, and that's exactly what's happening. So if you, in fact, even over GR, if you write K times PR, even if everything is defined over R, take a minimal parabolic defined over R, then it is true the same thing is true if P is a minimal parabolic defined over R. But the minimal parabolic defined over R has a compact part continues to be there, namely the intersection of this. Anyway, so these are facts you have, and then so and the assertion I made is that once GQ by PQ by gamma is finite is statement which I more or less proved. So this is a theorem. A detailed correct proof is given in my book, assuming that it's an L subgroup. From that one deduces it. It makes use of a so-called Brouillard decomposition. The proof in my book will make use of Brouillard decomposition. Okay, Brouillard decomposition over Q. The point is every element in GQ can be written as U, W, B, where U and B are in PQ. Use that fact, and that W is a Coxeter group, etc., etc. So this is finite, and a corollary of as a corollary of this, Borel deduces the following theorem. Yeah, before stating the theorem, let me introduce some more notation. So once again, G some simple algebraic group over Q, and P a minimal parabolic. Then P we know is can be written as ZS times N unipotent radical of P. Now let me denote by A the set. This is the identity component of identity connected component of SR. SR will break into finitely many components. SR is after all product of one dimensional tori, which means it's R star cross R star cross R star, so some L copies, and you just take R plus, which is the connected component, R plus power L. I'll call that A. Notice that all the eigenvalues of A, any character on A on T takes positive values on A. Okay. Chi of A is greater than 0 if A is in A, chi in the character group of X's. Now we have introduced this P determines a set of positive roots, positive Q roots. Decomposed like this, you remember n, the P gives you automatically unipotent radical n, which has all the positive roots sitting in there. So, and therefore get also a set of simple roots, simple Q roots. Simple Q roots are defined exactly as you do in the algebraically closed case. Q roots. Once you have positive roots, you say a root is simple if it's positive and cannot be written as sum of two distinct positive roots. And then it's an elementary exercise to say the usual proof which works in the algebraically closed case goes through without any problem. The only feature which is different from the case of algebraically closed fields is that sometimes if alpha is the root, 2 alpha can be a root, or equivalently half alpha can be a root. The only multiple of a root alpha is either 2 alpha is alpha itself, or 2 alpha or half alpha, plus minus of course always. But if 2 alpha is the root, half alpha is not going to be root, and if half alpha is the root, 2 alpha is not going to be root. 4 alpha cannot be root, so that the only multiple of alpha that can be root is either 2 alpha or half alpha. Those are the only multiples. So get also a set of Q roots and G, simple roots, which are denoted delta. With this definition, I'll introduce two further sets. For a number t greater than 0, A sub t will be the set of all elements t in A with the condition that, A in A with alpha A less than or equal to t. This is the kind of thing we did in the case of SLN, the Minkowski fundamental domain. The condition was AT was A1 by A2 less than t, A2 by A3 less than t. Here those are the simple roots, and here I am making demand for all the simple Q roots. And for c greater than 0, I will denote by n sub c the set of elements n in n. Notice that, let me put it like this. For I less than j. What do I mean by this? I choose a basis of the real algebra with starting with the basis of n plus, followed by a basis of zs, followed by a basis of n. And with respect to that basis, add n necessarily becomes triangular, because add n is mapped into itself. P, n maps P into itself, but the commutator falls into n. So because of that, everything becomes upper triangular. You can choose the basis for n also, so that everything is upper triangular. So once it's upper triangular, I want to make this for I less than j, I want this less than or equal to. Below I greater than j, it's either 0. If I greater than j, it is 0, and I equal to j, it's 1. It's a unipotent element, it's 1 along the diagonal. It's exactly what we did in the case of SLN. The off diagonal entries have to be less than or equal to half. I don't even have to say for I less than j, because some of the off diagonal matrices are automatically 0 anyway for I not equal to j.
So if n is upper two-line matrix,
Hmm?
its adjoint is also upper two-line matrix.
Sorry?
If n is upper two-line matrix,
No, a priori I do not know that n is upper triangular. Okay, because it's some maximal, it is unipotent radical of maximal parabolic group, and I know because it's unipotent, it can be made upper triangular if you like, even in the given basis, but that would also amount to add, after all, is a faithful representation. And the whole the algebra, the add is a faithful representation of the algebra, and on the unipotent group, even at the group level, it's faithful, because the faithful representation, whether I take them as matrices in the given representation or in the adjoint representation, it makes no difference for this. It is just simply some relatively compact set essentially. Either I can, if this relatively compact set, if you take the modulus in the upper triangular matrices, take the modulus of the upper triangular matrix, there will be some other constant perhaps. All these elements will be contained in upper triangular matrices with bounds on the off diagonal entries, which is maybe a different constant. The two are the other way around also. If the upper triangle, if as an upper triangular matrix it has a bound, is there a bound, there will also be the add of the upper triangular matrix will also have a bound. So anyway, so these are, notice that NC is compact. It's a closed bounded set in N. N itself is a closed bounded set in matrices if you like. So this is a closed bounded set, and so NC is compact. AT is not compact because things can go to this alpha A can go to 0. In SL2 for instance, you have T inverse. If T square goes to 0, but then T inverse will go to infinity. So it won't, it's not going to be compact. Okay, however, what is true is, the statement is the following: there exists T greater than 0 and C greater than 0 such that K A T N C gamma arithmetic group. So I should say there exists T greater than 0 and a finite set psi GQ finite such that K T N psi gamma is all of G. This psi of course depends on this, means you are taking this domain this set K A T N C, translating it by a certain finite number of elements, that after translation you take the union of those, apply gamma, you get the whole of G. We did the same thing for SLN except that there was no psi. And that is because, as I have already pointed out, the number of SL and Z conjugacy classes is the same as all Borel subgroups there. It exhausts here. A gamma conjugacy class may not exhaust it. In fact, even in case of SLN, if you go to a subgroup of finite index in SL and Z, you will need something like this. Sigma, in fact, sigma can be taken to be a complete set of representatives in GQ for the double coset space we know this is finite, You just take sigma to be a finite set of representatives. The proof of this is not difficult. However, it requires some more background. You need to know something about representation theory, finite dimensional representation theory of G, or an arbitrary field kind of as positive characteristic. And that representation theory again is very parallel to what happens in or an algebraically closed field. You have the highest weight theory. It's something very parallel, but you have to be a little more careful because highest weight is something character only on the torus, and you have to know, you have to start with something which is the representation of ZS. That's a compact group times a torus. You have to start with representation of that, and then you can develop a parallel theory, completely parallel theory. And then in the case of SLN, we started with minima. We took the standard representation, and then took an element G, translated by elements of gamma, and applied it on various vectors, and took a minimal vector on which of minimal length among these. That's what we did. The standard representation is one of the so-called fundamental representations of SLN. And basically, what's happening is that then we took the second vector, which was such that if you leave out E1, then it is minimal. That's the kind of thing. But that amounts to saying that E1 exceeded E2 is minimal vector in the exceeded second power, and goes on inductively. It amounts to E1. These are the exceeded powers are all the fundamental representations. So your successive minima using fundamental representations, and something similar can be done here, and that's what Borel does in his book Group Arithmetic. It's in French. In that book, Borel gives a proof. I will not go into the details. It's imitating the Minkowski method. Naturally, there are complications. Minkowski starts with the minimum for one representation, and then essentially, though he doesn't say it, he looks at the minimum for the next representation. E1 exceeded E2, and E1 exceeded E2 exceeded E3. That's the way he's looking at it.
This G is GR, right? G is such that GR.
Oh, sorry.
And one other thing, just this AT in the definition, alpha belongs to delta for all alpha in delta.
Yeah, I have not said that.
Okay, I understood it, but just
no, alpha. It's of course it's essential, or you can say all positive roots.
yeah, alpha.
You cannot have it for both positive and negative. That's the thing you have to be careful about. Sure. For all alpha and delta, that's the condition. So Borel's, and then what's the immediate corollary? It says that K, G mod gamma, GR mod gamma has finite Hermitian. Why? Because each of these sets has finite Hermitian. Oh, sorry. I'm sorry. No, this I said it wrong. I should say here. Yeah, so I should define PC, not C. The minimal parabolic, I should take points PR. The point is, first I should say here, notice that, so this should be PR by gamma intersection PR. Oh, sorry, it's once again I have to be careful. Let me write. I have to introduce one more group which I should have. Let me write PC first. Yeah, let me introduce P0. This is the following space. This is going to be, you look at pi inverse of m where pi inverse, let me write pi m where m, see m is got as far as look at zs, m is a subgroup of zs such that which is the kernel of all characters on zs defined over q. Take all characters defined over q and take their kernels and look at the intersection of all the kernels, that by definition will be m, and p0 is pi inverse pi m. So here is the situation, you have p, you go modulo u n, this zs maps isomorphically onto that. This is after all the decomposition of the so-called Levy decomposition of p as a reductive group times its unipotent radical. So when you zs intersection n is trivial, so this maps isomorphically onto that. And inside here I have taken a group m, I look at the image, this is pi, I look at pi m and take pi inverse. The reason for looking at this thing is the following: if you look at pi inverse pi m, which is p0, p0 by p0 intersection gamma is compact. This is because of the so-called Godma criterion. You notice that p0q has no unipotent elements. p0q has no unipotent elements, and therefore p0 by p0 intersection gamma is compact. It's reductive. It is, if you have a reductive group which has no unipotent elements, there is no unipotent q rational elements, and you also need the fact that there are no characters on p, no non-trivial characters on the group, which is true of m. By very definition, there are no non-trivial characters on m. Okay, so here it should be KATPC. That's what happens. And now from this it follows that dr by gamma has finite Hermitian. The reason is that each of these sets KATPC has finite Hermitian. PC is, oh sorry, I didn't define PC. Okay, sorry, P0. So I should write P0C. P0C is a set of elements P such that Pij in modulus is less than C. I am assuming G is a matrix group. So P is also a matrix. PC0, P in P0R and Pij. Basically some relatively compact set. Some compact set. It's a compact set. No, it's a compact set modulo P0 intersection gamma. They are not compact in itself, but modulo. What am I talking about? Sorry. This is a compact set. After all, P0R is a closed subgroup in SLN because P0R has no characters. So it's sitting inside SLN. It's a closed subgroup SLN, which is the closed subset of all matrices. So it's a bounded closed subset in all matrices, therefore compact. This is compact. So here is this KAT and a compact set here. This whole thing has finite Hermitian. Basically, you can again replace this KATPC0 by a compact set. You can replace this by a compact set inside the Iwasawa decomposition. Look at the Iwasawa decomposition. In N, you take a compact set. That's good enough because the rest of it can be switched across AT and absorbed in the compact group. P naught C is after all ZT, P is after all ZT times U, and there is a compact part of ZT which the whole of ZT can be taken out to the side, but what looking at a compact part of that will be in K. So it's essentially the same inverse order combination. It will be Ka, a compact set in C. That's what each of this is. Okay, and no, it's not quite. It's not quite correct. I'm sorry to say that, because there can be a. I have not said this. I'm not saying it right. You see, what happens is this. Well, roughly, let me put it like this. Inside PC0 is a compact set. KEAT PC0 I want to say has finite Haar measure. This is not quite. This is not a product decomposition. There's a part of NC here, and you'll have to get part of that across AT to this side, and then you get some compact set times AT times this, which you have to prove has finite Haar measure. The point is the Haar measure looks like this after all looks like R plus cross R plus cross R plus, and if you look at the Haar measure, you can write the Haar measure on K times Haar measure on this part times not quite the Haar measure but multiple of the Haar measure. That multiple takes care of making it this set AT into a finite measure. What happens is the Haar measure itself looks like dA1 by A1, dA2 by A2, etc. dAn by AN. That's the kind of thing that happens. It gets multiplied by some pi ai power ni. So what happens is such that ni minus 1 is greater than 0. Once you have that, the integral is going to be finite. These ai's are such that ni minus 1 is greater than 0. Sorry, ni minus 1 is strictly greater than minus 1. This ni is strictly greater than 0. So dA by a power r, if you integrate with r strictly less than 1, the integral is finite in the range we are interested in. You don't get into log a, you get some power of a, and that does the job. See, if it's ni minus 1 plus 1 ai between by ni minus 1 plus 1, sorry, ni minus minus 1 plus 1 between c 0 and c, 0 and t. That's what it look like. And the moment ni is greater than 1, the moment ni minus 1 is greater than 0, you are in good shape. This will be a finite integral. It's only at 0 you can have a possible problem, but once I know that ni minus 1 is greater than 0, you are done. In fact, ni greater than 0. Once you know that ni is greater than 0, we know that ni minus 1 plus 1 is greater than 0, and you will be done. So, as I said, I am not going to go into the proof. I refer to Borel's book where it is done, because otherwise it takes me way out talk about representation theory at some length. So, arithmetic groups therefore are very well understood, and okay, the thing is that if G, so if G is a Q semi-simple group of Q rank 1 and gamma is an L subgroup, then a similar theorem holds. Then one has G, oh sorry, GR. I'm not assuming that gamma is arithmetic. It's just an L subgroup. I'm not making an assumption. GR turns out to be equal to K AT yeah, sorry, either G by gamma, GR by gamma is compact. I don't have to say Q. G is a real semi-simple algebraic group of R rank 1. R rank 1 means maximal R split torus has dimension 1. It's a group defined over R, algebra group over R of R rank 1, and gamma is also a group. Then GR turns out to be equal to gamma K AT. Oh, here, yeah, there exists T greater than 0. Then either GR by gamma is compact, or there exists T greater than 0 and C 0, such that and maximal unipotent subgroups UI I in it's a finite set such that UI by UI intersection gamma is compact and K A T sorry, UI intersection is compact yeah, and R split tori Ti normalizing UI such that K AI T eta I where AI the set of elements A Ti of R yeah AIT TIR alpha A less than or equal to T. The group is of rank 1. So, there is essentially only one character, okay, which once I fix the unipotent group, there is a positive character makes sense. That is AIT, eta I compact in UI such that eta I UI intersection gamma is all of UI. So, exactly analogous statement. Now, I cannot talk of unipotent groups over Q. Unipotent groups over the Q have the property that if you look at R points modulo integral points, the quotient is compact. For unipotent groups, the quotient by integral points is compact, but here I cannot talk of Q points or Z points. So, I have to just simply talk of UI intersection gamma. I have finitely many unipotent groups normalized by certain tori, one dimensional tori, such that k at ait corresponding torus times eta I, which is a compact set, this gamma equals T. That statement holds. Now, because my assumption is G is of R rank 1, this I didn't have to introduce P0C. The point is P itself becomes centralizer of torus, one dimensional torus times unipotent group, and the one dimensional torus, the centralizer is equal to T times a compact group, and that compact group can be absorbed in K. So, because of that I do not have to say this. So, this is the theorem in the case of rank 1 group. Here I make no assumption of arithmeticity. I assume that it is an L subgroup. We know that arithmetic subgroups are L subgroups. So, in particular it is true for arithmetic groups in a rank 1 semisimple group, in a real rank 1 semisimple group, and for higher rank, if it is arithmetic, I know the theorem is true. But this is the there is no, I mean, in the higher rank that we don't assume, we assume arithmeticity, but it turns out that there is no loss of generality, because there is a theorem of Margulis which tells you that every lattice, in fact every L subgroup in higher rank semisimple group, real higher rank semisimple groups, is automatically arithmetic. See, whenever you have a group over a number field, this is a device by which you make it a group over Q itself. You get a natural group over Q, and its real points will be like, if you, what happens is you Q root 2 has two embeddings in R, one which takes root 2 into the positive square root, one which takes root 2 into the negative square root. Okay. Corresponding to this, you have a diagonal embedding as SOQ root 2 into see, the vector space looking at this Kn plus 1 can tensor this over Q with R. This is what you are doing, you are tensoring Q root 2 with R, and then it breaks into R cross R. You tensor take the form the tensor product with Q root 2 tensor R over Q is R cross R, and Q root 2 is sitting diagonally here, and that is how I decompose. When I project to the two factors, I get okay. And then, so SYFR is sitting inside. How do I get this? This is how do I get this? This is saying that SYF is in GL, sorry, yeah, F is a quadratic form over K. So, a priori you have SYF sitting inside GL and K, and therefore, if you look at this goes into GL and R cross GL and K tensor R. There is a natural map, then goes into GL and R cross GL and R, because K tensor R is R cross R. So, you find that SYF R will go diagonally into this. In one component, it goes into compact orthogonal group, sorry, it should be n plus 1. Here SYF is in GL n plus 1 K. In one component, this SYFR becomes a non-compact group, in the other component becomes a compact group. And we are looking at SYF of OK, the number field. This goes into Q points, the group over Q. The group over Q is those which leave invariant these two functions acting on Q2 n plus 1. I am looking at these two functions, extend everything to reals and then or complex numbers, and then what you want is a function, is a group acting on C2 n plus 1 preserving this map as well as this map. So SO of k, OK goes into q points. Oh, sorry, into z points, I should say. K points will go into q points, OK points will go into z points. This whole thing. And this was a discrete group with compact quotient. What we did was to say that this image here, you've got a group over k. If you look at the q points, it is simply the same as k points. K points, SOF, k points is the orthogonal group. In one embedding, it goes into semi-simple elements. Therefore, it goes into semi-simple in every embedding because the Galois conjugation takes it. Therefore, the element is semi-simple. So every element of every k rational point is semi-simple, or every q point of this group is semi-simple, which is the condition for the quotient to be compact. And then you can, so it's what's happened is this. So SOF OK is co-compact, discrete in SON1 cross SON plus 1. You get a discrete subgroup of this product. Project modulo this compact group. It will still remain discrete. In the project modulo compact group, the image of a discrete group is going to be discrete. Okay. So you get a discrete group in SON1. And the quotient is here the quotient is compact, so in the quotient also, when you go to SON also the quotient is compact. That's how we constructed a discrete subgroup of So you could therefore construct discrete arithmetic subgroups in a very nice way in SON1. Now, from this one can construct a group which is not arithmetic but co-compact. The idea is this: you take F1, F2, two quadratic forms in the following fashion. F1 is F thermal sum, a one-dimensional form, lambda, and F2 equals F direct sum mu. Lambda greater than 0. We are working with F1, F2 forms, quadratic forms over q root 2. F itself we have taken the form F is sigma xi square I equal to 1 to n plus minus root 2 xn plus 1 square, and therefore this F1, or maybe I call them lambda 1 and lambda 2. F1 is sigma xi square I equal to 1 to n minus root 2 xn plus 1 square plus lambda 1 xn plus 2 square. Where lambda 1 and lambda 2 are elements in, I can even take them in Q, makes no difference. I want to choose lambda 1 and lambda 2 in such a way that this quadratic form, this positive definite form, is not equivalent to this positive definite form. Sigma xi square plus lambda 2 xn plus 2 square must not be equivalent to sigma xi square plus lambda 1 over Q. Over Q they are not equivalent, or maybe over Q root 2 they are not equivalent. I want to make sure that they are not equivalent over Q root 2. So maybe I call this form f1 prime, f2 prime. So we assume that f1 prime not equal to f2 prime over k. These are forms over q root 2. So I want to ensure that these two are not equivalent over q root 2. Now what happens is this. So you have you look at G. I was looking at SOF1 and SOF2 over R. So isomorphic to SON plus 1 cross SO plus 2. Both are isomorphic orders. And they both act on the unit disk. This is the group of isometries of the unit disk with the constant curvature, negative constant curvature metric. This I make this act trivially, only that factor matters. So you have the unit disk on which you have two discrete groups operating. Notice that both of them have a common part. That is, if you look at sigma xi square minus root 2 xn plus 1 square, this is common to both. So that means you have an n plus 1 dimensional subspace, codimension 1 subspace, a disk like this here, in which such that the subgroup which stabilizes that in one of them or the other is the same, namely the group integral matrices in this part. Okay, so you have the big groups gamma 1, which is SO F1 OK, and gamma 2, which is SO F2. Both these operating on the space. Now, and there is this hyperplane in which their intersection, so to speak, which is this group, is going to operate. So this is gamma, which is SO F. Now look at all this in the quotient. In the quotient, what happens is this whole one quotient looks like some compact manifold like this. The other quotient, this is by quotient by gamma 1, which I call M1, quotient by gamma 2, which I call M2. And in here I have a submanifold, namely the projection of this. And similarly, here's the manifold. You can ensure that the group acts without fixed point, both the groups act without fixed points on the quotient, and if an element gamma in either of the groups fixes this, it belongs to the common subgroup. This is by passing to a subgroup of finite index, you can manage all this. Okay. Once you do that, you cut this along this. So it may break into two parts, or it may remain connected. One can't say. It could be like this, for instance. Okay, or it could be can cut into two parts. Whatever it is, if it's like this, if it remains connected after cutting, you get two pieces like this. And here you probably get two pieces like this. Now glue this to this and glue this to that along the boundary. It can be done in such a way that the constant curvature metric lives after the pasting. Why? Because there is the reflection in the hyperplane is an isometry. Because it's an isometry, you find that a boundary here is and these two are isomorphic. We know that the same group operates, the quotient is the same. So these two submanifolds are the same. Isometry is the same, and you have a product here, a collar here, a collar here, and when you cut it, this has probably been this collar has been separated into two. You get this part, and which you can think of as this here, and you're pasting it, which is like you're pasting here, so metric is preserved. Okay, so you get a constant curvature metric on the new space. You paste this part there and that part there. Okay. Now, the point is, if the group is arithmetic, what's happening is this: you take. Huh?
What are you doing?
See, as I take this part, I cut this and open it up, and this cut up maybe in two parts. Maybe here also it doesn't break. Maybe it's like this. But if it is like this, for instance, I paste this onto this, but ensuring that what I get is a space of constant curvature. That's okay, because the reflection is an isometry. Reflection here is an isometry, and so when I paste here, I'm as if I'm taking this part and identifying it with this part here. I'm taking this part and identifying it with this part, and so I'll enclose this whole thing into this, and so you get an isometry, so you constant curvature. Similarly here, if it's breaks into like you map this here, glue this here. In any case, you get a constant curvature space. And the point is that this new constant curvature space, because of the way we assume that f plus lambda 1, where is it?
F1 prime not equivalent.
F1 prime is not equivalent to F1 prime. You can conclude that this is not arithmetic. The point is, if it were arithmetic, what happens is this: all these elements which, there are elements gamma which keep this, how do I say this? After cutting, you have elements which still preserve this but do not belong to the subgroup. There are elements, when I cut this up, before cutting it up, you have some isometries which preserve this, but there are other isometries which, how do I say this? I'm not saying it right. Let me see how to rephrase it. No, the kind of contradiction one gets is the following.
So F is not arithmetic.
No. After gluing, you look at the fundamental group. That is actually a lattice which is not arithmetic.
Because after gluing, I get a compact manifold with constant curvature. So the universal covering is the unit disk with constant curvature, and therefore what you get is a discrete subgroup of this SO n plus 1 again. You get a discrete group. This group, I want to say, is not arithmetic. Okay, and I don't remember the details. It's not very difficult. At this point, you just use the fact that this what I called F1 prime, F2 prime, they are inequivalent. Will tell you that the group cannot be arithmetic. If the group is arithmetic, it will force it to be either this or that. Since there can't be both. I mean, if they are equivalent, of course it can be both, but they are not equivalent, so it cannot be both. That is the statement. I don't remember the details now. It's quite simple to prove this, and this, there's a whole lot of examples. You can find lots of pairs lambda 1, lambda 2, which are inequivalent quadratic forms, positive definite quadratic forms, which such that f1 prime is not equivalent to f2 prime. Plenty of examples, and therefore you get infinitely many examples. But the original examples given in 1960s by Windberg, and Makarov. I don't know I've never studied Makarov's example, but Windberg had a elaborate theory about reflection groups. You have groups generated by reflection, so-called Coxeter groups. Okay. You have some number of generators of order 2, say a finite set of generators S of order 2, and such that S square is 1 for every one of them. And if you take two elements SS prime is of finite order or can be infinite order. SS prime has an order PSS prime, where PSS prime is either some integer or infinity. Such a group with such relations, you take the free group on that finite set and pass the quotient by normal subgroup generated by these relations, then you get a group which is called this pair is called a Coxeter system. And now you take a group of space of constant curvature. On this, the isometric group operates. And now you can talk of reflections, that is, those which leave a hyperplane invariant and take one to the other, which is what we use here. Those are isometries. So if you can put this, take the Coxeter group, and suppose you can put this inside one of these isometric groups of constant curvature spaces, and then pass to the quotient. You can ask the question whether the quotient has finite measure, is compact, and if it's compact, is the group arithmetic. And Windberg gave an elaborate criterion of when the quotient is compact, when it has finite measure, and non-compact. For each one of them, he had a criterion. And then next stage is to ask whether it's arithmetic, for which also he gave a criterion. Everything in terms of the matrices PSS prime. He had a complete theory. And with that, he was able to give examples in SO31 and SO41. He couldn't go beyond that. And in fact, he had another paper in which he proved you definitely cannot go beyond 10, because from SO10 onwards, no group generated by reflections is a lattice. He proved such a statement. And so the only group generated by reflections were totally useless. But these are arguments for case when, his general theory is very beautiful and works for SO31 and SO41. Hello. அது இல்லை பண்ண முடியல, சரியாக வேலை பண்ணல, இன்னைக்கு பண்ணுறேன், இப்போ சாயங்காலம் பண்ணுறேன், நாளைக்கு தான் வரும். இப்போ ஆமாம். Sorry. Yeah. Okay, so Windberg did this, but it's a very beautiful paper where he describes completely when you group generated with reflections, and the idea there, it imitates Poincare. Poincare constructed the fundamental domain for in the case of SL2R, which is same as SO21. For this discrete group acting on it, you construct a similar fundamental domain for groups generated with reflections following Poincare. And then if that fundamental domain is relatively compact, then the quotient is compact. Then when it is a finite measure, this is the kind of thing he has to deal with. Okay, so much about non-arithmetic groups. I don't think I'm going to say more about it, but the example is very simple to describe. Proof also is not very difficult, but it's I can't remember it now. I don't remember it now.
These are examples on the quotient as finite.
Yes. The same thing you can do with, we started with the quotient compact. You start something with the finite measure quotient, you can imitate the same thing. You take one with finite measure quotient, one with compact quotient, do the same thing, paste, and then you will still get the middle thing should have compact quotient. Okay, the one which you cut, that has to have compact quotient, but the big one need not have compact quotient. If one of them has no compact quotient, use the and take a compact quotient and glue, it will remain non-compact. It will give you non-arithmetic lattice. And then the next natural question to ask, okay, then and Margulis proved the theorem when the rank of the semisimple group is greater than 1, then every discrete group is arithmetic. So the only groups real rank greater than, if you have a semisimple group of real rank greater than 1, actually you'll have to say, yeah, real rank greater than 1, and gamma is a lattice which projects into dense subgroups in every factor. It should project a dense subgroup in every compact factor. That's necessary. Irreducible lattice. It should project to a dense subgroup in every compact factor, and if there is more than one non-compact factor, then also in every non-compact factor, every factor should project densely. That's the condition. Okay, under that condition, he proved it's arithmetic. And then the only question left was, suppose the group is real rank 1 and simple, is the group arithmetic? Open question. The example has been given for a discrete non-arithmetic group. An example is given by SU 21. You see, this is the group of complex analytic automorphisms of the unit disk in CM. See, this is a case of C3 or C4, which is C3, I suppose. Complex two-dimensional disk. That's the situation. Two-dimensional complex, which is real 4-dimension. On that, a non-arithmetic subgroup was first constructed by Mostow, and then Mostow-Deligne did a more elaborate work that exhibited a countable family of infinite family of discrete groups. You cannot expect an uncountable family. There is a theorem, a so-called rigidity theorem, which tells you can't deform a discrete group continuously so that it is not conjugate to itself. If you have this theorem, maybe I should speak about it, and I'll do it next time, which is the rationale for why people thought that practically all groups are going to be arithmetic. That's what people thought. And rank greater than 1, rank greater than 1 has been proved. The statement is following: gamma in G, a lattice, assume that either G has more than one non-compact factor, and the projection, well, G a lattice, G has no compact factors, let us assume. G has no compact factors, which you can assume without, because you can project modulo the compact factors and still get a lattice. So if G is a lattice, gamma in G is a lattice, G has no compact factors, assume that either G has more than one non-compact factors with projection on every factor, projection of gamma on every factor dense. Or that rank G is simple over R, and R rank of G is equal to 2. Then if rho T gamma to G is a family, is a continuous family of homomorphisms, of gamma in G with rho 0 T in the unit interval, with rho 0 the inclusion of gamma in G, then there exists epsilon greater than 0 and GT continuous map of minus epsilon plus epsilon into G such that GT gamma rho naught gamma GT inverse equals rho T gamma for every T, for every gamma. If you try to deform the group a little bit, it will ends up in being its conjugate. Obviously, if you can get a one parameter family by conjugating by a curve inside G, but what this says is that that's the only way it can happen. So this clearly indicates that you can't have a continuous family of discrete groups with compact quotients. This is true if more than one compact factors, or that G is simple and not isomorphic to, locally isomorphic to SL2. Well, R rank, I don't have to say that. R rank is G is greater than or equal to 2 is what I said. In fact, so sorry, G is simple. No, R rank G is not equal to 2 is not necessary. G is simple and not isomorphic to SL2R locally. That is, it's not SL2R or PSL2R. Suppose that's the case, even if rank 1 is also okay. For example, S1, these groups are rigid. You can't move them in a continuous way without conjugating them. The only way you can move them is by conjugating them. Okay. This is what suggests that the family of discrete subgroups with compact quotients or with finite measure quotient, they have to be only countable. There's only countable possibility because you take all homomorphisms of gamma in G. Okay, what will that look like? You gamma in G, if you take a homomorphism F rho of gamma in G, this means what? Gamma, we are looking at something with a finite measure or finite compact quotient. You can show such things are finitely generated. So this becomes a quotient of a free group by some normal subgroup, and it's even finitely presented, so the normal subgroup can be taken to be finitely generated. So if you take the space of all homomorphisms gamma in G, that simply becomes a subset of G cross G cross G, as many factors as the number of generators of the free group. And then you have some number of generators for n, and each of those elements can be thought of as a word in the free group, and then you can evaluate that word. If it's the word is say F1, F2, FR, F1, F2, FR, F1 per R1, F2 per R2, etc. You take the corresponding element here and map it in G1 per R. So you get a mapping into. This is the number of generators for n as a normal subgroup, and this is number of generators for F. So here is a smooth map phi, and the fiber over identity is your space. It's some analytic, it's an analytic thing, it's some relative set. And in a relative set, I am saying every connected component is necessarily got by conjugation of some element, of this element. So anything in the connected component of gamma is necessarily actually in semi-simple group actually is an algebraic group structure. So this mapping is an algebraic morphism. So phi inverse is an algebraic variety, real algebraic variety, and it has only finitely many connected components. And you are looking at those connected components in which there is a discrete group with which is a lattice. And if I have proved that lattices cannot be conjugated nearby, it shows that the connected component is trivial. It's the orbit, nothing more. Each connected component will have to be orbit, and there are only finitely many orbits. So this tells you it's a discrete family. All discrete groups with compact quotients is going to be a countable family, because you fix gamma, you get countably many possibilities. And this also tells you immediately that you can conjugate gamma into algebraic numbers. G is, you can take G to be an algebraic group. A priori it's an algebraic group of complex numbers, but then it becomes one knows that anything over complex numbers is already defined over some number field, because you have it over Q. You take, I mean, there is the, if you have take an algebraic group over complex numbers, there is already this so-called Chevalier structure which makes it into a group over Q. Okay, so it's already a group over Q, and so what I have done, it shows you what you have is a variety defined over Q. Okay, and therefore it is any variety defined over Q has points in Q bar by the Nullstein adds. So the open each the orbit of any element in our case is going to be open in its closure, because nearby. So because of that, you find that in the open orbit there will be a algebraic point. So everything is going to lie in a number field. So the whole thing falls into G of algebraic closure of Q cross G of algebraic closure of Q, so much. So it's a countable set. So set of lattices is certainly a countable set in dimensions in other than SL2. SL2 there is a family, because you have Riemann surfaces. SL2 by discrete groups of SL2 give rise to Riemann surfaces, and Riemann surfaces are moduli. So in fact this is what SL2 had moduli, and they wanted to first see if there are moduli for for others. For instance, take the unit disk and take the quotient, you get a complex manifold of dimension. Say I'm taking a unit disk in C2, then take a discrete group in a compact quotient, and you can ask whether it has moduli, and this tells you no way, there's going to be no moduli for that. And this is why people thought maybe everything is arithmetic. And so it was a hot thing in the 1960s when this guy Winberg and Makarov came up with examples of non-arithmetic groups. Now, of course, afterwards, Margulis came up with this beautiful proof. That was in 1984. No, it was 1978. No, it's 1974. He came up with this beautiful proof of arithmeticity. And then, of course, the only cases now left to be examined are the case of so-called rank 1 groups. And even in the case of disk in complex n space, it is wide open except n equal to 2. The question is wide open, and it looks quite intractable. There's no. I tried something, maybe I'll tell you about it at some point, but it didn't work. I mean, I still think there is something there, but I'm saying that despite the fact that I told this to Gromov, and he disposed it off as not a good idea. But I don't think, I think he was being rash.
But this Gromov-Piasecki-Shapiro construction cannot be carried out in.
No, the point is.
Constant curvature is not present, so you don't know what the universe is covering.
No, the point is that, see, these are totally geodesic submanifolds which you get, and the reflection is an isometry. In the complex stage, there will be no codimension 1 submanifold. There is only codimension 2 or complex codimension 1, and then it is not clear what to do with that. and you don't have isometries which you can use, which will keep that
You get some mix.
submanifold stable, and and if you cut along submanifold, you don't get two things like this. You don't get a manifold with boundary which you can paste. It's not clear, but of course that is too naive. Maybe one should try more complex geometric methods, but it's not clear. And the point is, obviously there is some difficulty, otherwise Gromov would have carried it out.
Of course.
After all, he is a geometer. I think I'll stop here. So next week, before I think I will speak about compact forms of general symmetric spaces before I talk about non-arithmetic lattices. And even arithmetic lattices, it's going to be, maybe I will not start on that, because week after I'm not here.
Yes.
I'm going back, and then I'll come back in the first week of March. At that time, I'll talk about arithmetic. Next time, let me see what I'll think of what I should. Yeah, maybe I'll prove the rigidity theorem.
Okay.
May not prove it, but give some
Indication.
indication of how it's done.